All right, I'll start from the beginning. No, just to remind you of what we talked about, lots of fun things happening in machine learning, lots of different ideas. Neural nets are really exciting, but they have limitations. And so what can we do? Well, we can think about other approaches like, viewing machine learning as probabilistic modeling, and we have Bayes' rule that comes from the sum product rule. And, it doesn't preclude us from doing neural nets if we want to, if we distinguish between models and algorithms. And so we can do things like Bayesian neural nets, and that might be useful because representing uncertainty is useful, and it's useful in science, in industry, and all sorts of other places, flying cars as well. I talked about this sort of like vision of automating machine learning. And then I spent a few minutes talking about probabilistic programming as a framework for defining probabilistic models and having inference done automatically on those probabilistic models. So are there any questions about that? Any questions about yesterday's lecture? Everybody's forgotten. I can start again. All right. So I was saying that I wanted to cover 3 of these topics that I'm really excited about. So the second topic is called Bayesian optimization. And so what is Bayesian optimization? Bayesian optimization is trying to solve the following problem. It's a very general problem of optimizing a black box function that is expensive to evaluate. Okay, so there's some function f of x, and we want to find the optimum. And the problem is we can't afford to go evaluate it 10,000 or 100,000 times, because maybe every time we evaluate the function, it costs effort or time or money or something like that. Okay, so that function, for example, could be the efficacy of some new robot design. And so evaluating the function might actually involve building the robot and seeing whether it works or not. Okay, so you want to minimize the number of such experiments you do. I said, global optimization, we'd like to ideally find the global optimum of the function, but of course, in general, that's going to be very hard in high dimensions. So that's the problem Bayesian optimization is trying to solve. And the solution is kind of interesting. And basically, the solution is to treat the problem of optimization as sequential decision-making under uncertainty. Okay? So think about it. Most of the time, people talk about optimization. They say, okay, there's some algorithm. You run the algorithm, and we can maybe analyze the properties of the algorithm. But what is that algorithm doing? That algorithm is actually making decisions, right? That algorithm says, I evaluate f at x, and then I decide, I compute the gradient maybe or something like that, and I decide to go this much in this direction and evaluate f at this point, etc. So all these algorithms are actually making sequential decisions. And where's the uncertainty coming from? Any ideas? So I'm just trying to optimize something. Where is the uncertainty? You look like you want to answer. Yeah. If I knew where the global optimum was of my function, I would just go there, right? So the uncertainty comes from the fact that until I evaluate f at a particular point x, I don't know what f at that x is, and I also don't know what the derivatives are, etc. So this is a funny kind of uncertainty. A lot of people are uncomfortable with this kind of uncertainty, because it's not that the function that you're evaluating or optimizing is random. It's certainly not random in most cases. And you might even have like an analytic expression for that, what that function is. But until you evaluate that expression, your system doesn't actually know what the value is going to be. Okay? So this is a funny kind of uncertainty. Bayesians are perfectly happy with this kind of uncertainty, but a lot of other people are not, because you maybe have the analytic form of the function, so you kind of know everything about the function in principle, but you don't really know it until you actually evaluate it. Okay, that's the kind of like philosophical answer to how to do optimization. And this has just a huge number of applications. Basically, use your imagination, go beyond machine learning, think about places where optimization is used, in the real world in some way. Like, even settings where, for example, you're doing A/B testing of some design or something like that, or, like you're trying to do drug discovery, for example, is an application that we've looked at. Okay, and of course, you could use this to do machine learning as well. So in more detail, what does this actually involve? Well, here is Bayesian optimization in a nutshell. This is a slide my former postdoc, Matt Hoffman, produced, so thanks to him. But it sort of very nicely describes what's going on. So, so the top curve, the top plot is meant to show you the function that you're trying to optimize and the information that you have so far about the function. So what's going on here? Well, imagine that we have evaluated the function at a bunch of points. These are these round circles, okay? And so x is on this axis and f of x is on this axis. We've evaluated the function at a bunch of points. This is at some point in our Bayesian optimization. And we've gained some knowledge about what f of x is at these points. You can, for example, imagine that evaluating f of x gives you maybe a noisy estimate of f. So what we have in the shaded region here is a representation of my current knowledge about the function based on the evaluations that I have. So the blue line might be my mean estimate of the unknown function f, and the light blue shaded region might be two standard deviations of my uncertainty in the function. So note a couple of interesting things. At the places where I've evaluated my function, my uncertainty in the function is low. And in fact, if I assumed that my function was noise-free, it would shrink down to 0. It would pinch down to 0 at the points that I've evaluated. Away from where I've evaluated, my uncertainty is higher. So that's why you get this sort of wiggly pattern. Okay, so given that information about the function, we as humans could ask ourselves, well, where do we think is a promising place to evaluate next? And there are different ways of measuring how something is promising. So we could say, given what we know about the function so far, what's the probability that if we evaluate at some other point along the x-axis, we will get an improvement? We will get a point that's higher than any of the points we've observed so far. That's a sensible thing to ask. And you might imagine that if I evaluate the function here, the probability of improvement is very low because I kind of know that the function is low here. I'm trying to maximize. Whereas maybe if I evaluate the function here, the probability of improvement is high because I have a lot of uncertainty. The function is generally high. And so there's a chance that the value might come out higher than any of the other ones. So that concept is sort of like that measure, probability of improvement, is one criterion I can use based on my uncertain knowledge of the function to decide where to evaluate next. When I say I mean the algorithm can use that criterion, probability of improvement. Or I could talk about expected amount of improvement. This is a different criterion. Expected improvement is another criterion. Or what about information gain? I could say, which points give me the most information about the location of the maximum? And that's another criterion. Anyway, the criteria by which I'm going to make that decision are are called acquisition functions in Bayesian optimization. Okay, so how does the algorithm actually work? I start with some initial sample, some points that I've evaluated. It could be no points, it could be a few points. And then we initialize the model. The model is some model of the unknown function with uncertainty estimates. Then we compute the acquisition function, which tells us where is the next most promising place to evaluate. And that's the thing shown in green here. What you can see is that for this particular choice of acquisition function, which might be something like expected improvement, I'm not sure, the most promising places are around here. Okay, so let me just, these spots are aligned. So around there is the most promising place to evaluate next, and that makes sense. Around here is not a good place to evaluate. Or around here is not a good place to evaluate. Around here is not a good place to evaluate because we already know that the function is sort of lower there, although we still have some uncertainty. Okay? Does that make sense? Now, the assumption is that evaluating the real f of x is very expensive, but in the inner loop, what we can do is we can find the optimum of this acquisition function. So we're actually going to have an inner loop which is optimizing the acquisition function. That's cheap because that's something I'm numerically storing on my computer. I find an optimum or approximate optimum or a good point, and then I evaluate the real function there. And so I get a new point. And then I iterate this process. Any questions about that? Yep. Okay, the question was, in Bayesian optimization, does the initial model have to be Bayesian to capture uncertainty? The real answer is no. Okay, really the key idea here is that what we need is a representation of the uncertainty in the function. So you can use a Bayesian approach or you can use a classical approach. What you really need is a representation of uncertainty because your acquisition function is going to be based on that representation of uncertainty. And so the Bayesian optimization literature is actually exactly parallel to the multi-arm bandits literature. In fact, these two communities are pretty much solving the same problem with slight differences in the style that they write the papers. Okay. Yeah, next question.
Sorry, is the acquisition function trying to maximize information gain point, trying to best point that like solve?
So that's another great question. There are about half a dozen papers proposing different acquisition functions, and they do different things. Okay, so some of them are very greedy acquisition functions, which say, I'm going to go for, like expected improvement is a very greedy acquisition function. It says, I'm going to go for evaluating the point that is expected to most improve the current maximum that I have. And that's a good acquisition function if you are going to stop immediately after that. Okay, that's why it's quite greedy. I've worked with, and I'll mention that a little later, I've worked with some colleagues, Miguel Hernandez Lobato and others, on other acquisition functions that are based more on information theory, where you ask yourself, I want to evaluate the point that is expected to give me the most information in terms of bits about the location of the maximum, which might not be the next bet for the maximum. Depends on the structure of your model. And other people have tried different acquisition functions. So there are about half a dozen good ones out there, and they make a bit of difference. Okay, so now what's the correct way of solving this problem? You know, for every well-posed problem, there is a correct way of solving it. Okay, and that way of solving it might be intractable. So any thoughts on that? Well, it's a sequential decision problem, and we have a beautiful theory for sequential decision problems under uncertainty. That's sort of like in the framework of things like Markov decision processes and POMDP and so on. So the correct way of solving this is if we happen to know the horizon, like how many, let's say we know how many evaluations we are going to do before settling on a single value, then we would work backwards from the end, and we would solve not the greedy problem, but we would solve the multi-step decision-making problem from the back. So there are ways of trying to solve this that are just, you know, horrendously expensive and not very practical, but it's useful to think about, like, well, what is the principled way of actually solving the problem of optimization? The other thing is that obviously the solution depends on the cost of evaluating f of x, right, our real function, versus the cost of doing all this inner loop computation. So at some point, if the cost of evaluating f of x is cheap, then it's not worth doing any of this stuff, right? Because you're spending a lot of compute time, you know, thinking, whereas you should just be acting and evaluating. Okay? So you have to trade off the cost of thinking with the cost of acting. Okay, so that's Bayesian optimization in a nutshell. Why is this important? Well, I mean, I think it's a good framework for thinking about any optimization problem. Not necessarily like actually doing it, but just to think about what does it mean to optimize. It's especially useful, as I've highlighted, if evaluating the function is expensive, because you're thinking about where to evaluate next. It's also very useful when evaluating derivatives is hard or impossible. Now, you can do Bayesian optimization with derivatives. That's blindingly obvious, actually, if you know this area well. But if evaluating derivatives is hard or impossible, then you just have to try evaluating f of x at various points. So that's quite useful. It's useful when you're doing optimization if there is noise in the function evaluations. A lot of optimization algorithms just, you know, just crumble in a heap of mess if the function that they're trying to optimize is noisy. Of course, stochastic gradient descent methods and so on inherently are doing noisy function optimization, right? But generally, if there's noise in the function evaluation, you want to be able to incorporate that. It's useful when there may be possibly noisy constraints. So you're doing optimization with constraints. It's useful if you have some prior information about the function that you're trying to optimize. Okay? So, for example, there was a beautiful PhD thesis by Valentin Dalibard, where he was actually using, it was quite crazy, he was using probabilistic programs as models of the function that he was trying to optimize. And the reason he was doing that is that he was trying to optimize computer systems, and he could actually put in quite a lot of prior information into the behavior, the sort of things like latency and time and so on of a different computer system design, and he'd use a probabilistic program to represent that, which gives you error bars, which then you can use for Bayesian optimization of that system. And it's also useful if one needs to optimize many similar functions. Okay, so basically optimization is learning, right? Because here we're learning about the function as we're trying to evaluate it. If we have to optimize many similar functions, then you can think of this as multitask Bayesian optimization. Okay, so essentially you've learned to optimize this function. Now we're going to optimize another similar function. And so we can transfer from one to the other. All right, so that's why it's important. And you know, the sort of results that you get are basically, these are for, like, for example, for different acquisition functions. This was kind of your question earlier on. There are many different acquisition functions. People develop new acquisition functions. So, for example, this is Bayesian optimization under constraints. And here, the actual thing that we're trying to optimize is classification. We're trying to minimize classification error of a 3-layer neural network constrained to make predictions in under 2 milliseconds. Okay, so this is a constrained Bayesian optimization. We have to come up with, each evaluation is, you come up with a new architecture, and then you can either figure out whether it satisfies the constraint or not. And if it satisfies the constraint, you might want to see what its validation error rate is. And these are just two different acquisition functions. This is this is expected improvement with constraints, and this is predictive entropy search with constraints. And predictive entropy search is an information cost function. And different things work better and worse. I won't make a big deal out of that. Okay. All right, so that was Bayesian optimization. Any questions about that? Yes.
Many Bayesian optimization methods use Gaussian processes to model the cost function. I would like to know your opinion on fixing the hyperparameters of the kernel or inferring the hyperparameter space of data.
Yes. Very good question. There are two parts really to that question. First of all, I think it's important to surgically separate the concepts from their general implementation. So there's nothing in Bayesian optimization that says you need to use Gaussian processes. It just happens that Gaussian processes are kind of a useful tool for modeling unknown functions, and they give you good uncertainty estimates. But people have written papers where they do Bayesian optimization with, random forests, and they do Bayesian optimization with neural networks and probabilistic programs, as I mentioned before. So just separate the concepts out. However, it is true that like the vast majority of Bayesian optimization papers use Gaussian processes to model the unknown function. The question was really about hyperparameters, and I think it's a really good question because one of the things you really care about in Bayesian optimization is learning about an unknown function from very little data, okay? Because the whole point is collecting function evaluations is very expensive. So you need to have reasonable estimates of the unknown function from very little data with good error bars. If you fix the hyperparameters, then on the good side, you can't overfit the hyperparameters on the small amounts of data. But on the bad side, those hyperparameters might be not very good. So it might take you longer to optimize the function. If you optimize the hyperparameters, the good thing is that eventually you will adapt to learning the properties of the function. The hyperparameters tell us things like the length scale and vertical scale of the function and various things like that. You adapt to the function, but you might overfit early on. That can get you in real trouble. So there is not a simple answer in that it's actually kind of a trade-off. The ideal thing would be to be Bayesian about the hyperparameters and average them out, which is a bit more expensive. Yes? Briefly, okay, I'll repeat the question, sorry. The question was, could I briefly describe how you deal with constraints in Bayesian optimization? So there we have a JMLR paper, which is all about that appeared recently. You can look that up. The basic idea is you are trying to model the function itself, but you also need to model the set that satisfies the constraints. Okay, so basically you have several models, one for f and another function for each of the constraints. And you could say the unknown, for each constraint there is an unknown function which is trained essentially like a classifier. So for any x, this let's say f sub c of x for constraint c, if it's greater than 0, it means the constraint is satisfied. If it's less than 0, it means the constraint is not satisfied. So when you evaluate at a particular point x, you might learn about f of x, but you might also learn about f sub c of x, whether the constraint is satisfied or not. So you're simultaneously learning these things. And there are lots of games you can play with that. Like you might be, for example, in the neural net case, figuring out if the neural net architecture makes predictions in under 2 milliseconds is very easy. So evaluating the constraint is very cheap, but evaluating the classification error is very expensive because you actually have to train the neural network and then look at the classification error. So you can trade off the relative cost. Okay. Let me move on to talk about the automatic statistician. This is sort of like the third thing that I'm going to talk about as, in this theme of automating machine learning. So the problem this is trying to solve is that, we have a lot of data analysis problems out there, and there's huge value to those data analysis problems, but there really aren't enough data scientists, statisticians, and machine learning experts to go around, even if we have lots of summer schools like this. It's still not enough. So the solution is automate you guys, basically, and me. Well, less facetiously, the solution is to develop a system that automates some aspects of the process. And the interesting aspect that we're trying to automate here is model discovery from data. So a lot of what people end up doing is try out different models on data, but can we come up with a framework that automates that process? And the ambition is actually much broader than that. We would love to be able to automate a lot of what people do, which is feature engineering and pre-processing, searching over models, discovering a good model. That seems like a really nice thing to do. But then, interestingly as well, we would love to automate the process of explaining what has been discovered to the user. Because one of the problems in machine learning is that a lot of machine learning is just a black box that produces predictions, and a lot of uses of data science, machine learning, and statistics are places where people want to understand where the predictions come from. Your ultimate client is going to say, well, in the loan application setting, you might actually have a legal imperative to be able to explain that decision due to the general data protection regulation, which I just mentioned yesterday. Or in other settings, people want to understand, well, where did this come from? Okay, so we're going to try to do the opposite of black box machine learning, call it transparent box machine learning. The machine learning system is going to do a lot of thinking, and then at the end of the process, it's going to produce a report that tells you exactly what it discovered and why it claims what it claims. Okay. So this is the basic idea of the automatic statistician. It's a research project, really, so that I could spend the next 10 years kind of doing projects related to this. In fact, if you're interested, we have a number of postdoc positions at Cambridge University and also at the Alan Turing Institute relating to aspects of the automatic statistician. So if you don't want to move to San Francisco, you can move to Cambridge or London as well. Or you can stay in lovely. Okay, so here are the ingredients of the automatic statistician. The idea is you have data, it comes in, and then you're going to try to search over models of the data, okay? And in this case, we're actually going to think about probabilistic models of the data. But it's not a question of like, I'm going to enumerate 6 different probabilistic models and evaluate those 6, and that's it. We want to do something much more exciting and interesting than that. What we want to do is we want to have an open-ended language of models, and then we want that language of models to be expressive enough to capture models that people would commonly use, but also we want it to be open-ended in the sense that we should be able to generate models that nobody's ever tried. The reason we're calling it a language of models is a little bit like, language itself, where you can take words and combine them together to form new sentences. Okay, so we should be able to generate new kinds of models by combining other model components. Then, of course, what we end up with is a huge space of models, an exponentially large space of models to search through. So that seems quite painful. So we need a search procedure to efficiently explore this language of models. I'll describe each of these components in the next few minutes. Then we have another problem, which is, we have all of these models, we have our data, and the system needs to decide what's a good model for the data, right? Ultimately, that's what model discovery is all about. So we need a principled method for evaluating models. We need a method that will trade off the complexity of the model and the fit to the data. And there are various things one could do. The sort of obvious thing that maybe most of you are familiar with is one could do cross-validation for that. And cross-validation is a reasonable approach for finding good models from data, but it's actually rather expensive because you have to then do cross-validation in every part of the space, and also it's not very data efficient because you have to hold out some of the data to do that cross-validation. And the other thing about cross-validation is you can certainly overfit if you're basically then fitting to your validation data. The interesting thing is that what we're going to do instead of something like cross-validation is we're actually going to use Bayesian Occam's razor, the marginal likelihood, as a way of evaluating models. This is trading off complexity and the fit to the data. And then I'll show you that that actually works. Okay. And then the last bit is we want to be able to explain what we've done. So we need to have a procedure to automatically explain the models. So make the assumptions of the models explicit in a way that's intelligible to a non-expert. Okay. I'll show you examples of all that. Now, the tool that we're going to use, which has been mentioned before, underlying some of the work, not all of the work in the automatic session, but some of the work, the sort of oldest published work, was based on Gaussian processes. And we've sort of moved on from there. We've tried many different other kinds of things. But I think it's a useful point for me to explain what a Gaussian process is. I'm going to spend about 3 slides on Gaussian processes. So consider the problem of nonlinear regression. Okay, so you want to learn a function f from some data. The data are these magenta points. The function is a mapping from x inputs to y outputs. And given the data, what you'd like to learn is a representation of the underlying function with error bars representing your uncertainty. Any function approximator would do as long as it can give you a good representation of uncertainty. Now, a Gaussian process is a particular idea. It's actually a very old idea, sort of over 100 years old. It's a way of defining a distribution over functions which can be used for this sort of Bayesian nonlinear regression. Now, the word process confuses people sometimes because a lot of the times the word process is used, it's used in the context of temporal things, right? Like stochastic, Gaussian process is a kind of stochastic process, and stochastic processes, if you're familiar with them, often the examples people give are of essentially functions of time, functions that evolve in time and things like that. So don't be confused by that term stochastic process as implying time. Again, if we distill what the concept of a process is a collection of random variables indexed by some space. That space could be time, but it could also be space. It could be the inputs of your function. It could be anything. It could be any dimensionality you want. So Gaussian process is indexed by x, and x can be anything you want, any dimensional you want. Clearly, it could be time. Right? Any questions about that? Like there's spatial processes. For example, if you want to model the temperature over locations on Earth, then you could think of that as a spatial process indexed by locations on the sphere, right? Okay, so we're going to do, roughly speaking, Bayes' rule in function space. So we have a prior over functions, we have a likelihood, we multiply the prior by the likelihood, and then what we get is a posterior over functions. Okay? Now, what's the definition of a Gaussian process? Where does the term Gaussian come from? Well, P of f is a Gaussian process if for any finite subset of points, call them x1 to xn in the sort of domain of this function, curly x, the marginal distribution over that subset, P of bold f, so f is now an n-dimensional vector, is multivariate Gaussian. Okay? So here is the way to think about it. You all know about univariate Gaussians over one variable, bell-shaped curves. We can have multivariate Gaussians, which are over n-dimensional vectors, which have a mean and covariance matrix. The infinite dimensional generalization of that is a Gaussian process. Okay, Gaussian process is the infinite dimensional generalization of a multivariate Gaussian distribution, where if I evaluate it at a finite number of points, then I get multivariate Gaussian. Yes, question? Yes. Okay. Can you connect the multivariate indexing to this finite subset notation? Okay. So let's take x to be the unit interval, okay, between 0 and 1. And now I can take 7 points on that unit interval. 1, 2, 3, 4, 5, 6, 7. All right. Then I can look at f of x at those 7 points. So f of x1, f of x2, f of x3, f of x7. That's a 7-dimensional vector. Okay. Now, what I'm saying is that imagine that that 7-dimensional vector had a multivariate Gaussian distribution. What does that mean? That has a 7×1 mean, which is the mean of the function at those 7 points, and a 7×7 covariance matrix, which, if the function is smooth, will mean that nearby points are more correlated than faraway points. Okay? Now, if I look at the interval between 0 and 1, and I think about functions on that interval, right? Like that function there, I could evaluate it at 7 points, or I could evaluate it at 700,000 points. That would be a 700,000 dimensional vector. If you take the limit of that argument, basically the function itself is an uncountably infinite vector, in a sense. I know that sounds wrong, but basically it's sort of like if you discretize things, it's a vector, but you have uncountably infinite number of points that you could evaluate it at. And now so what is a Gaussian distribution in that uncountably infinite space? That sounds scary, but the good news is that exists if you take any finite number of points, and when you evaluate them, you get a multivariate Gaussian. If all of those multivariate Gaussians are consistent with each other, then there exists something which is called this Gaussian process that lives in the space of functions. Okay, it's a long answer, but I don't know. Answered the question? The index is the set 0 to 1. The index set is the set 0 to 1, basically. Sorry? Yeah, that's fine. Yeah. Or the index. I mean, it's a one-dimensional index set, but because there are uncountably infinitely many points in that set, the Gaussian distribution in that is a Gaussian process. The index set could be points on the planet Earth, right? You could have spatiotemporal Gaussian processes, like do points on planet Earth over time, for example, for temperature patterns. Okay, so that's the Gaussian process. The good news is, even though it's an infinite dimensional quantity, if you only evaluate n data points, right, then all of your computations are basically linear algebra computations with n data points. That's why people use Gaussian processes, because it's really simple to write down the equations for how to do learning with the Gaussian process. You can do analytic Bayesian updating of your unknown function as you get more and more data points. Okay? And all of those operations are bits of linear algebra. They're operations on n-dimensional Gaussians. So Gaussian processes can be used anywhere you have unknown functions. And in machine learning, there are many places you have unknown functions. When you're doing regression or classification, when you're doing ranking, you can do dimensionality reduction, et cetera, et cetera. So there are literally dozens and dozens of papers that use Gaussian processes for this stuff. And if you like TensorFlow, for example, there is now a very nice Gaussian process library called GPFlow, which basically allows you to combine Gaussian processes with any other bit of TensorFlow to do learning in models that are maybe hybrids of Gaussian processes and neural networks. So that's Gaussian processes, I think, in one slide. I'm going to do a little bit of a further description of Gaussian processes. So I like to make these diagrams. A lot of you have probably seen me present diagrams like this if you've seen me give a talk. And the diagrams start with simple concepts, and from them you get more complicated concepts. So the simple concept we're going to start with here is linear regression, the most important idea in all of statistics and machine learning. Right? You've got to know what linear regression is. So we start with linear regression. It's some way of mapping from x to y. And then we can think of 3 different operations to make a cube of things that we could do to linear regression. So here is one operation in magenta. We can turn a regression model where the output is a continuous quantity into a classification model where the output is a discrete class label. Okay? So for example, we can turn linear regression into logistic regression. This is just an example of something that lives on this corner of the hypercube. There are other examples like, probit regression or other forms of classification here. Perceptrons, let's say. Okay, so we can turn linear regression into, for example, logistic regression by replacing that continuous output with something that gives you a probability over a discrete class label. Okay. Those are the magenta arrows. We could take any model like that and treat it in a Bayesian manner. So those are the blue lines. So Bayesian linear regression, what that is still the same model as linear regression, but instead of optimizing the parameters to maximize, say, likelihood or something like that, or minimize squared error, what we're going to do is we're going to treat the parameters in a Bayesian manner, and we're going to try to do integration over those parameters. We're going to infer a distribution over the coefficients of our linear regression. The nice thing is that for linear regression with Gaussian noise, we can do that analytically. We have Gaussian priors on the parameters, so it's really like simple. Do that, and that would be called Bayesian linear regression. Okay? And now the orange arrows are uses of the kernel trick. Again, something most people are familiar with in machine learning. We have some lectures on that. And that is, instead of doing the linear regression in your original space, map it to some high-dimensional space, called the feature space, and then do the linear regression in that feature space. Okay? That's really called the kernel trick, because in that case we can do this without explicitly going into the feature space by computing a kernel. Okay? So that would be called kernel regression. And now with these 3 operations, we can get a lot of interesting models. So Gaussian process regression, which I just talked about on this slide, can be thought of as Bayesian kernel linear regression. So, you're doing Bayesian linear regression, but in this feature space. Okay? And exactly the same kernel that appears in kernel machines is the covariance function that's used in Gaussian processes. Okay, all the same properties have to hold, basically, for those two things. So that's Gaussian process regression. Models like support vector machines are kernel classifiers. So they're classification models done in a feature space, but they're fundamentally linear in that feature space. So support vector machines live on this corner of the cube. I've talked about everything here. So what lives in this corner of the cube? Well, this is Gaussian process classification. So now instead of a regression model where my output variable is continuous, I can then map that through some final nonlinearity, turn that into probability of a class label, and then what I get is kernelized Bayesian classification, which could be thought of as a Bayesian analog of support vector machines, or it could be thought of as a kernelized version of Bayesian logistic regression. Okay? So all these ideas are related, and it's sort of useful to see how they're related. Yes? Yeah.
Yeah. I mean, just like when you explained the Gaussian and then the kernel seems, I mean, for the kernel it's just an feature space. And then you said like if you do it with Bayesian, then it's like a Gaussian process. So I didn't get.
Yeah, it's a little subtle. Obviously, I actually have like a whole lecture on Gaussian processes, and I've compressed it into 2 slides. So it's not. It's okay that it's a little bit difficult to follow. The basic idea is okay. So can people see if I write on the board here? So how did that? Okay. So the way you think about Gaussian processes, you say F is drawn from a Gaussian process with some mean M and some kernel K. Just like we could say a vector V is drawn from a multivariate normal distribution with mean M and covariance matrix, let's call it K this way. Okay, so it's analogous. So in this case, you have a vector drawn from a multivariate distribution. In this case, you have a function drawn from a Gaussian process. So what does this have to do with kernels? Let me just try to explain that. So what this statement says is take F evaluated at 2 points. At the point X, so I have X, and I have this quantity, which is F of X. And at another point, X prime, so I have this quantity, F of X prime. Okay? Take F of X and F of X prime. Those are 2 points. I can make a couple of statements. So for example, it's a distribution over functions. The expected value of F of X is M of X. It's the mean function. And the covariance between F of X and F of X prime is K of X, X prime. And that's the kernel matrix in there. And what that really means, so every time I see a kernel, I think about covariance functions, because that's the only way I can understand what a kernel actually means. Kernels mean something in the world of Gaussian processes. They're a statement about how correlated is F of X and F of X prime as a function of, for example, maybe the distance between X and X prime. Okay? And usually a lot of kernels have the property that they're decaying functions of the distance between X and X prime, which encodes the concept of some sort of smoothness in the underlying function. However, the concept is much more general than that. So again, the concept here includes Bayesian linear regression. That corresponds to the linear kernel. it includes periodic functions, where you actually are quite correlated at various levels of the period. It includes polynomials, so that's where the polynomial kernel comes from. So Bayesian polynomial regression, etc. So maybe, hopefully that's answered the, yeah. You can, by the way, the index set doesn't need to be the real line. It could be strings. And then what you have is like you just throw in a string kernel, and then you have a Gaussian process in the space of strings or graphs or whatever you like. So again, you know, one needs to break free from the typical uses of these things. Yeah. You could, okay, the question was, you can also use a neural network as a kernel. There are various ways in which you can combine Gaussian processes and neural networks in interesting ways. You could take a neural net and transform the inputs before feeding into a Gaussian process, which involves basically the neural net being hyperparameters of your Gaussian process. And you can do other things. And in fact, my next slide is, I think, about the relationship between neural nets and Gaussian processes. So thank you for that question.
Excuse me?
Yes?
One question about like the orange shadow represents the kernel tree, no?
Yeah.
What's the benefit from that kernel tree? I mean, I know that you can pass to work from with infinitely many features. Is there some other benefit?
The benefit of the kernel trick is fundamentally that if your function is nonlinear in the inputs, then what the kernel trick allows you to do is to represent nonlinear functions, but by doing computations that are essentially linear in this high-dimensional space. So it's an easy way of doing nonlinear functions. Neural nets are a more difficult way of doing nonlinear functions, but they're more adaptable because you could think of the initial layers of a neural net as adapting the kernel, say. Okay. Neural nets. I did mention neural nets, so here it is. So, so here is my familiar neural network again. And if you remember, in Bayesian neural networks, what we had is we have a mapping from x's to y's. We have some parameters that are the weights of our neural network. And basically what we're going to think about is what happens if we have a distribution over the parameters of the neural net, and we try to do Bayesian inference over those parameters. So this is just, you know, the Bayes rule applied to neural net parameters. That's Bayesian neural nets. Now, the interesting thing is there is a beautiful relationship between Bayesian neural nets and Gaussian processes. This was discovered by Radford Neal in his PhD thesis, published in '94. And that relationship is that if you have a neural network with one hidden layer, okay, looks like this, infinitely many hidden units. Okay, so something most, you know, people don't do, but take the limit of infinitely many hidden units, and then use Gaussian priors on the weights. And in fact, it doesn't have to be Gaussian. They just have to be independent and sort of by the independent and sort of finite variance, and by the central limit theorem, you're going to get this result anyway. But just think of Gaussians because it's easier. Then that Bayesian model corresponds to a Gaussian process. So what does that mean? That means the thing that we care about, we don't care about the crap in the middle here. We care about the input-output relationship. Okay? The input-output relationship captured by that class of models is exactly a Gaussian process. Okay? And there are a bunch of interesting consequences of that. One of them is, at that point in the early 90s, people had been using neural nets and had been getting frustrated by what a pain it was to optimize and the question of how to choose the number of hidden units and stuff like that. And Radford Neal came along and he said, you don't have to do any of that. You could you don't need to choose the number of hidden units. You can have infinitely many hidden units, and it's just 2 lines of MATLAB to do that, and you can do all the computations analytically and do Bayesian inference and get the error bars. So we don't need all this neural network stuff. And some gullible people like myself thought, wow, this is beautiful. I can forget about neural networks. And so many of us started working on Gaussian processes as general ways of modeling functions. Yeah, question? Yeah, so the question is, I'll just repeat, what is the covariance or kernel that corresponds to this? And the interesting answer is, it depends on the form of the activation function of the neural net. So, for example, in, I'm not sure, yeah, I think in Radford Neal's thesis and then in a follow-up paper by Chris Williams, people talked about the neural net covariance function, which was basically if you have a tan H nonlinearity at the level of these hidden units, that corresponds to a particular covariance function that has a particular weird form. Right. And you can play that game with many other covariance functions. Okay. Radford, always being way ahead of his time, he also analyzed infinitely deep networks. So you can find that in his thesis back in the early 90s. Okay. So that's the relationship between Gaussian processes and neural nets. The subtlety is that neural nets, if you have multiple hidden layers, then they can do interesting transformations of the data along the way, and all of those are learned. Whereas if you use a Gaussian process, if you give yourself just a fixed kernel, then essentially what you're doing is the kernel in all kernel machines is really determining how you generalize from data, right? It's determining, how similar is f of x to f of x prime as a function of the difference between x and x prime, 2 inputs. So ironically, these infinite neural networks are in some ways not as flexible as finite but deep neural networks. Okay. And the reason is, they are flexible in that, in theory, if you're just interested in theory, we can model any function arbitrarily closely with a Gaussian process, basically. But in practice, for finite amounts of data, we have a shallow sort of architecture that doesn't really learn interesting features. Okay, so that's Gaussian processes. Okay, raise hands. Are you happy with the pace that I'm going? I'm going to give you a binary choice, faster or slower. Okay, so if you don't know, just choose randomly. Should I go faster? Should I go slower? Okay, faster wins out. All right. Okay, so here is the automatic statistician for regression and time series models. Remember, that was background material on Gaussian processes. We're going to use Gaussian processes in this automatic statistician with this sort of pipeline. And the basic idea is we're going to be, in this case, I'm going to be looking at time series models and trying to form explainable models of time series models. And these include, basically, we're going to base our framework on Gaussian processes, where Gaussian processes have kernels. And what we can do is we can compose new kernels by combining other kernels. And the base kernels that we have in our language, or atoms of our language, are, for example, the squared exponential kernel that corresponds to smooth functions, the periodic kernel that corresponds to periodic functions, linear kernel corresponds to linear functions, the constant kernel, and the white noise kernel is just noise. So these are the base kernels. And then the nice thing about kernels is that you can combine kernels with various operations that keep the space of kernels closed. So that's addition and multiplication, for example. So here's multiplication. If you multiply a linear and a linear kernel, what you get is a quadratic kernel, which corresponds to a distribution over quadratic functions. So by closure, our language concludes all polynomials. Okay. If we combine linear and periodic, we can get trends with sort of linear trends with periodic functions, something that's commonly used in time series modeling. We can get locally periodic functions by multiplying squared exponential by periodic, etc. And we're also going to model what's called change points, where you're changing from one kernel to another because something has happened in your time series. And then the search procedure operates as follows. You've got some data. This is the time series. You start with some very basic model, and then you search over basic kernels. So this happens to be another kernel in the alphabet. This is called the rational quadratic. It fits the data. This is the extrapolation with error bars. And then as the search procedure continues, it takes the best model currently, applies different transformations to that to get other models, and then it keeps improving that way until at some point it stops. So this is the model that it ends up deciding on from this observed data, and that's the extrapolation that it gives you with error bars. Okay, so that's maybe already interesting. You know, why did it not stop here or here? Why did it go here? What's making this a better model? It actually stops at this model. Well, the thing that we're evaluating is this concept called the marginal likelihood. That's what we're evaluating at these points. And that's basically the Bayesian kind of computation of the probability of the data given this choice of kernel. This is saying this choice of kernel in the search is the best kernel that we could have. Now what we get is an expression for the form of model. And what we're going to do is we're going to produce a report that explains what that is to a human. So here's an example. This is now a different data set just for variety. This is airline passengers worldwide between the late 1940s and the early 1960s. That's what the raw data looks like. This is the raw data with the fit from the Gaussian process on top of it, with the extrapolations. And this is the executive summary produced by the algorithm telling you what it's found in the data. And that's basically by taking the kernel that is found and translating parts of the kernel into bits of text and putting them in a report. So it says it found 4 additive components, including a linearly increasing function. You can sort of see that. An approximately periodic function with a period of 1.0 years and with linearly increasing amplitude. That's a pretty good, I think that's a pretty good automatically generated explanation of what's going on in here. You can see the sort of annual periodicity, the sort of seasons, maybe that's summer or Christmas, I don't know. And then underlying that, there's a 4th component, which is a smooth function, and then uncorrelated noise with linearly increasing standard deviation. And that's kind of harder to see in these plots. But actually, if you look at the full reports, these are available on the website. The full reports are, you know, kind of 5 to 15 pages, formatted like NIPS papers. You know, this is just all computer-generated text that is telling you what it's found in the data. And it's kind of fun. I can show you maybe a little video of this. Okay, so this is our report writing demo. I keep threatening to put this back online. It was online for a while, but just sort of put it back online as a free sort of service where you upload data, it churns around, and it thinks about the data, and then it produces a report for you telling you what it's found in the data. We are going to do that. It's just that I have a few people in my group who are perfectionists, and they keep trying to add new functionality to this before we release it. So the report is being prepared. So this is an automatic report on the data set Iris. Instead of a PDF, we have it on the web now. And this is a bit fun. Actually, the report is dynamically generated. So it produces a report, but it now has evaluated a few more models. And what it's decided is this Iris data set, famous data set from 1936, the best model that it found for it was a mixture of 3 Gaussians. That's in the space of models that it was looking at. This is not using Gaussian processes now. This is kind of extended from there. It's a mixture of 3 Gaussians, and then it automatically produces some visualization. Sorry, this is somebody scrolling up and down the model. It automatically produces some visualizations, and then it also tells you why it chose mixture of Gaussians, because mixture of Gaussians had better, in this case, cross-validated log predictive density. So instead of marginal likelihood, in this case, we're using cross-validated log density. So it had better of that than, you know, lasso or independent Gaussian. Okay. So that's the basic idea behind the automatic statistician. It turns out that by systematically searching over different kernels, the performance of the automatic statistician in terms of predictive, here in this case, root mean squared error, is actually better than if you just throw a standard squared exponential or Gaussian kernel into a Gaussian process. And so these are kind of standard things you could do, starting with linear regression. And, you know, on these 13, over these 13 data sets, we're getting, you know, up to 3 times less error than just doing linear regression. Or this is Bayesian multiple kernel learning, kind of doing 1.5 or 2 times better than that, and so on. And so part of the story here is that I think when you automate the search over models, if you do that well, you're going to do better than a human. Because humans might be very clever, but humans are not very patient, okay? But computers can be quite patient, and, you know, a computer can basically, you know, parallelize a lot of that computation. Of course, ideally, you would combine the human and the computer. So the computer could do the sort of boring stuff, produce an initial report, then the human could, you know, put his name on the report and send it to the manager or whatever. Right. Okay. So, so these models can work pretty well. So in more recent work, we've built an automatic statistician for classification. Most machine learning problems are classification problems. Here is a report obtained from that. This was a master's project using Gaussian processes. And the nice thing about that is that the report for classification looks different than the report for regression problems or time series problems. Right? Each of these reports has to make sense for the kind of problem that you're trying to solve. And what the report does is the search procedure finds structure in the data. So it says the best model it found involved an additive combination of the variable plasma glucose and a 2-way interaction between variables pedigree, function, and age. This is in this diabetes data set. And then it report actually produces each variable and its importance using various metrics, and it also tries to verbally describe the relationships between the inputs and the outputs. The kind of classification scenarios we're thinking about are classification scenarios where you might have a few or maybe a few dozen input variables that have meanings of certain kinds, and you're trying to produce an output class label. And so you produce verbal descriptions like this variable provides little evidence of class label assignment given the baseline error, you know, or classification based on this variable alone is even worse than the naive baseline classifier, things like that. So you can really tell whether stuff is important or not. And we also, importantly, we look to see if relationships are monotonically increasing or not. And that's, I think, at the level of explanation that people care. Like, for example, there is a monotonic relationship between the variable plasma glucose and the diabetes outcome, monotonically increasing relationship. And so we can discover those automatically and put them in the reports. This is just more components of the report. I'll say 2 more things about this kind of general automatic statistician project, and then we can move on from there. So here is something that people don't do enough of in machine learning, and that is model criticism. Okay, So model criticism is an old concept from statistics. And the basic idea is, I fit a model to data. Are there aspects of the data that that model is obviously not capturing? Okay? Or are there assumptions in that model that are clearly not true of the data? So that's the kind of question that I think is important when you fit models to data. And a very, a very classical way of doing model criticism is, for example, let's say you fit a regression model, and your regression model assumed Gaussian noise. Well, when you look at your residuals, they should be Gaussian distributed. And if they're not Gaussian distributed, something went wrong, right? So you can do a classical statistical two-sample test to figure out whether the model assumptions were valid or not, whether they were significantly violated by the data. And so part of our ambition for the automatic statistician is that not only would the automatic statistician try to produce an interpretable report, but it should also do model criticism on itself, okay? Something that, we want to be better than humans, right? Something that most humans don't do is criticize themselves, so we're going to get the system to try to criticize itself. And if you look at the reports that we produced in the earlier work, there's always a model criticism section at the end, and we've done some work with James Lloyd looking at this sort of concept of statistical model criticism using kernel two-sample tests, which I think there's a lot more work in this area that can be done. Okay. So that's one concept. The other thing that is fairly important about the automatic statistician is that the search over the space of models is expensive, okay? So we're trying to discover good models from data. Maybe the data sets are very big. Evaluating every model on the whole data set is an expensive thing to do. And so we want to be able to be rational about the use of computational resources. And so as a sort of side project for that, we ended up developing methods for building machine learning systems that learn under strict time, CPU, memory, and disk space constraints. Okay? And the idea there, and so this was kind of also motivated by the AutoML workshop and the AutoML competition. And that competition is to design machine learning methods capable of performing all model selection and parameter tuning without any human intervention, which is kind of a good challenge. Okay. So essentially, that sort of thing works pretty well, and I can show you a video of that. So again, so let's see. This is now not in the context of Gaussian processes or clustering. This is now, what this is doing is just for that system that we built for the AutoML competition, where what we have is a bunch of different random forests and a bunch of gradient boosting machines, okay, and with different parameter settings. And the question is, we're trying to solve a classification problem. We have a limited amount of computational resources to do that. And we have a choice of many different models to try. So what are we going to do? So here's what we're going to do. The axis here is time in seconds. So we're going to allocate, we're going to pick one of these, and we're going to allocate a small amount of time, around 15 seconds, to evaluating that model. Okay? Sorry, I'm going to stop it again. So we spend 15 seconds evaluating that model, and we have a score for that model, which is maybe some held out predictive performance. And obviously that goes up as we train. And now we try a different model. Okay, and this is a random forest, and that's the curve for that random forest. And what can you tell me, just as a human, what can you tell me about this curve versus that curve? Which one looks more promising? Blue or red? Blue, right? Blue looks more promising. And you could tell that if you were playing around with things, with this experiment, which only took 15 seconds of computer time, you could tell that blue is looking more promising. So here is the way this is going to work. Based on 15 seconds of this learning curve, what we're going to do is we're going to build a Bayesian model that tries to predict what the learning curve might look like into the future. This is just a random sample. We're uncertain about the future. In fact, we're using Gaussian processes to do this. We're uncertain about the future, so we model this curve, we forecast into the future, and based on those forecasts, we're going to compute. So these are just some random samples of this forecast. I'm going to stop it again. Based on those forecasts, we're going to compute this quantity, which is estimated utility per time step. And that is the utility of putting more computation on that particular model. And actually what we're going to do is we're not going to try to choose the winner. We're not going to try to choose just the best of these. We're going to try to build an ensemble based on these models. So the utility is measured in terms of added additional utility relative to your existing ensemble. Okay? And that's the performance of the ensemble. So let's just watch how this works. So this is testing out the green model. Now it's testing out the purple model, which doesn't seem to be that promising. Okay, it's testing out the orange model. Again, not that promising, and says like orange is not very good. The yellow model, it's pretty uncertain, right? These things are jumping around because it's uncertain samples about the possible future, and so on. And now let's see what happens, because I think it gets interesting after a few more seconds. Once it's tried out everything a little bit, in this case it's just enumerating things. More sophisticated methods would actually try to generalize between these models. So it's now tried basically everything for about 15 seconds, and it's going to allocate computation to stuff that looks more promising. So currently the winner is this blue, but now the black looks most promising. The estimated utility for the black one is highest, so it keeps running with the black one, sort of racing along, happily saying, oh, this black one is pretty good, right? So just give it more computation time. And the ensemble performance is improving as predicted. And this is the total amount of time that we've spent, around 270 seconds or something like that. Okay, now the yellow one, etc. And some of the less promising ones, they're just sort of, they're stopped early, right? I think this framework just makes sense, right? There's nothing really, nothing really that crazy that we're doing. We're just trying to be reasonable about our use of computational resources. And to do that, we actually turn this problem, again, into a sequential decision-making under uncertainty problem. We have uncertainty about how useful these things are. We're trying to make some sequential decisions. Any questions about this? Yeah.
Is it a case where you have a link between Bayesian optimization and multi-arm bandit? This one.
Yeah. So this is, again, it's sorry, I guess it stopped. Yeah, again, you can analyze this either from the Bayesian optimization framework or the multi-arm bandit framework. They're kind of the same. Yep.
You're using GPs to forecast, is that
yeah.
In this case, you're forecasting using GPs. How are you forecasting?
Yeah. So the question is, how do you forecast these things? So actually, when we do this, we use GPs to forecast these learning curves. We use a particular kernel, which is inspired by a beautiful paper that really inspired us called free-thaw Bayesian optimization, which comes up with a kernel that kind of looks okay for learning curves. So you want to have a kernel that is a good kernel for modeling learning curves. And you don't need to use a Gaussian process for that. You could just have any model of learning curve that you want. The nice thing is that for many of these learning algorithms, as you give them more data and more computation, the learning curves are fairly predictable. I mean, of course, sometimes you can have big jumps, right? And that's harder to model, and that's why you need to have some uncertainty remaining in the models. Okay. So, so that's the end of this.
Sorry?
Yeah. Question? Yeah.
Yeah. I mean, those results look extremely promising. Would you say that this is the end of statistics or the end of statisticians and even machine learners? I mean,
of course, we would hope that, right? No. You know, the real goal is we need better and better tools, right? We need higher level tools so that we can do things that computers can't do. And the best analogy for all three of these things that I've talked about, probabilistic programming, some of this like automatic statistician, also automatic resource allocation, is what happened when people came up with compilers in computer science, okay? So people used to program in machine-level code. Somebody came up with compilers, which meant that you could write programs in a higher-level language, and then the computer would translate that to machine-level code, right? And now we are able to think at a much more abstract level about computation as computer scientists. So I think that the future of machine learning and data science and statistics should also be based on more powerful tools that can automate some of the reasoning, and then we can do quite high-level stuff, understanding things and exploring spaces of models and so on. Okay, good. So that brings me to the end of this lecture. I have, 6 more hours prepared in case anybody wants. I'll do some of it after lunch. But the framework that I've talked about is this probabilistic modeling as a framework for building systems that reason about uncertainty and learn from data. I've sort of briefly reviewed these things, and I kind of appreciate all the question answering and sort of interaction. I think that's a better way of talking about these things. I wrote a review paper. There was a very nice special issue of Nature on machine intelligence, and I wrote a review paper for that issue called Probabilistic Machine Learning and Artificial Intelligence, which you can find here. I'll send you the PDF if you don't want to go behind the paywall. And of course, we're hiring both in Cambridge and at Uber AI Labs in San Francisco, and also the Alan Turing Institute in London is hiring things related to all of this. I want to thank a lot of collaborators I've had, and I'll stop there, take some more questions, and I guess we'll break for lunch some more. Any questions? Yeah.
Hi. So I guess when you're choosing a model as a statistician, something that comes into it is a qualitative sense of the decision. You know that you had the iris data set, you know that's a biological data set, and you maybe think to yourself, right, okay, these kind of models have worked well on similar problems before. Do you see a future in embedding that kind of information into the search within your automatic statistician?
Definitely, yes. So let me just go back to this flow chart. The goal of the automatic statistician is more of a research goal than a practical goal. I mean, it's practical if you have somebody who just has data but doesn't know anything about what patterns there might be in the data. But it's not practical as a framework for introducing expert knowledge into your modeling, right? Whereas probabilistic programming is a really practical framework for introducing expert knowledge, but you have to be quite an expert to be able to write a probabilistic program. So they're sort of different. Now, the ultimate ambition that I have for the automatic statistician is not as a sort of one-shot thing where you upload the data and it produces a report, but more of a conversation between the person who has the data and the computer that's going to analyze it. And so the way I would imagine this happening is you could try to push the system into certain kinds of models by giving it some prior knowledge. And also the system might ask you questions. Like, you know, for example, you upload the data and the system says, there seem to be some outliers in your data. Here is a plot that indicates that row 72 and row 319 are very weird. Are these outliers? Should I ignore them? And then the analyst can sort of look at the data and say, oh gosh, yeah, somebody misrecorded the data. Yeah, let's remove that. And so this sort of conversational AI for data science is the way I would like to see this evolve eventually. And I think that would be really exciting. And I don't think there's any reason we can't do that. Just sort of like, you know, I need a room full of people like this who are interested in that, and then, you know, we, yeah.
Hello? Are there any guarantees for rates for Bayesian optimization?
There are definitely papers that look at analyzing kind of convergence properties for Bayesian optimization. I think those papers are interesting, but basically every time you want to get a guarantee, you have to make assumptions, obviously, and then the assumptions might or might not be met. But basically, in the same way that people have analyzed bandit algorithms and obtained guarantees, the same kind of the same style of guarantees can often be applied to Bayesian optimization. It's a little bit harder in continuous spaces, but you have to make some assumptions there. Yeah, I'm not an expert on it.
With the automated statistician, you're searching through this very large space of possible models.
Mm-hmm.
And you mentioned that you're somehow doing this evaluation. Could you talk just a little bit on how you trade off complexity?
After lunch. Yeah. Not because I'm hungry, but actually I have some slides that talk about that. The basic concept is this concept of the marginal likelihood, and it's it just follows from the sum rule and the product rule of probability theory, and it just basically says if you do all the Bayesian calculations, you don't have to penalize for complexity in any way. You don't have to regularize. It's sort of all built into some rule. Yeah.
Hi. I was reasoning about the Bayesian optimization approach, in which the uncertainty about the objective function is actually formalized mathematically and analytically. And I was thinking about the result of the optimization method, which is just an estimate or a point estimate of where the optimum could be.
Yeah.
So there is no uncertainty related to what actually the algorithm returns. And I was thinking how this could fit in a Bayesian vision.
Yeah, that's a great question. So at any point in Bayesian optimization, I have a representation of my unknown function as a distribution over functions. I've evaluated at some points, and I can represent that somehow. It might be expensive, but I can represent that. Often with the Gaussian process, which is what it is. Now, from that distribution over functions, I can extract the answer to any query you want about functions, including the distribution over where the maxima might be. So actually, One way to do that is the very old classical method called Thompson sampling, which some of you may have heard of. And that is, I have a distribution of functions. What I'm going to do is I'm going to sample, say, 1,000 times from that. And for each one of those analytically computed things, I'm going to optimize it. And that gives me a distribution over where I think the optima are. So I can actually compute it. It's just that it's expensive and people usually don't care. People in optimization usually formulate their question as, give me X star. They don't say, give me distribution over X star. But I could give them distribution of X over X star if that's what they wanted. Okay. Let's make that the last question.
Yeah, sorry, I'll be relatively fast. So since you're working in Uber AI Labs as well, and you mentioned the GDPR, I'm not sure if you talked about it yesterday. I wasn't able to attend, but how has the GDPR influenced your work there, changes that you've made, possibly models that you're going to use due to the transparency issue, and so on and so on? Yeah,
so I did mention it yesterday as well. It's a broader question that affects, I think, anybody who's doing machine learning in a setting where interpretability might matter, right? And so there are certainly places that it hasn't directly affected us. I mean, we haven't really implemented anything yet on the basis of that, but it's where a lot of people are very conscious of the fact that interpretability is going to be quite important. The big question is, what is interpretability? What is an explanation? And you might have a right to an explanation, but what is an explanation? And I'll give you a classic example, which I'm sure all of you are familiar with. If you go onto Amazon right now and you start shopping for something, it might recommend you something. And then sometimes when you have a recommender system, it actually tells you, it says, I'm recommending you this because you looked at this or you bought this previously, right? That's an explanation. But that's not actually what's going on, right? There's probably some gigantic deep neural network implemented in, MXNet somewhere that has like 7,000 features in it and so on. And that explanation is just something that is meant for the customer to get like a confidence about what's going on, right? And that neural network might actually be doing all sorts of, might not be a neural net, but let's say whatever that thing is, might be doing all sorts of inferences about like your race, or whether you're high income or low income, whether you have a criminal background or not. And there are like really good examples of this that actually people have discovered that, if you go searching on Google, there might be some racial profiling that's going on there, And obviously companies are very sensitive to this and they all try to avoid that. But the bigger question is, nobody really knows what an explanation is. So in fact, one of my colleagues at Cambridge is sort of writing a position paper on like interpretability in AI and machine learning systems. So I think that a lot of questions. The short answer is, it's on our minds, but hasn't affected the actual models that we use. All right. So let's break for lunch. Yeah.